Atoms lesson. So you first is J.J. Thomson's model. J.J. Thomson is a plum pudding model, where there will be this is an atom, where this itself is an atom, where the electrons are embedded in it. It's a positively charged atom, which is this, with electrons which are negatively charged embedded in it, which resembles a plum pudding, and he called it as a plum pudding model. But this was a failure, J.C. Thomson's model. Because it could not explain the origin of spectral lines. There were some spectral lines which got observed. It could not explain the spectral lines, and
Scattering of alpha particles.
it also couldn't explain the scattering of alpha particle. Okay. Okay, now Rutherford did the alpha particle scattering experiment, and he explained each and every point based on his theory, where he took a thin gold, he took a source of alpha particle. You know, alpha particle is radioactive, alpha, beta and gamma, so took it in a lead block. He took it in a lead block, and a source of alpha particle, in a lead block. He used a collimator to allow a thin beam of alpha particle to come out of this. It's called a collimator, and this was made to fall on. So then you have alpha particle, source of alpha particle placed in the lead block. Why do you place in lead block? Is radioactive, no? So keep in lead block, it will not come out. Okay, so then you have a collimator through which the beam of alpha particle emerges out, is made to fall on a thin gold foil, and the gold foil, what was noticed was scattering the alpha particles at certain angles, like this, like this, like this. They were scattering. The alpha particles got scattered like this. Some got even rebound. You know, so then there was a screen here, which is a zinc sulfide screen, which is called a detector screen. A detector consists of zinc sulfide screen, which is a scintillating material, where when an alpha particle falls on it, it will emit light. And so then there is also a microscope to observe that alpha particle, which is movable microscope, which you can see rotate about and observe the number of particles scattered and the angle of scattering. So then therefore they plotted a graph between angle of scattering and the number of particles scattered. I think it was between n and theta. N on the y-axis and theta on the x-axis. Number of particles on the y-axis and theta on the x-axis, and they found that it was inversely proportional. As the angle is becoming more, the number of particles is becoming less, by which they concluded that more alpha particles went undeviated. Scattering நடக்கலனா it went undeviated. So then what were the observations? More alpha particle went undeviated. I'm sorry about my bad handwriting. A few got scattered through a large angle. A very few got scattered even obtuse angle. Okay, which more than 90 degree. A few, about 1 in 8,000, got deflected more than 90 degree. Deflected through 90 degree or even more. 1 in 8,000 got deflected about 90 degree or more. So, but most of the alpha particle went undeviated. And a very, very few, occasionally, use the word occasionally, a few got rebound. An alpha particle gets rebound. These are the three observations, and this graph is very important. So from this, what did Rutherford conclude? Most of the alpha particle went undeviated. Other one, the observation. Conclusion: therefore, the atom consists of mostly empty space. That is why it's able to go undeviated. Second, 1 in 8,000 got deflected through large angle, from which he concluded that the nucleus, which is positively charged, is occupying the center, with the size of the nucleus being 10 to the power minus 10, while the size of the atom being 10 to the power minus 15. Which is smaller, 10 to the power minus 15, this 10 to the power minus 10. Nucleus is of smaller size than the atom, and the nucleus occupies a very little space at the center of the atom. That is why only very few got scattered through larger angle. That is the conclusion for the second point. And even the third point is nucleus is positively charged. It's positively charged. Look at the center. That the alpha particle is also positively charged. That is why it's getting rebound. Positive repulsion. So these are the three conclusions he made out of this Rutherford experiment. Are you clear? And then the most important points in this is why did he choose the gold foil? Why did he choose the gold foil? Because the gold foil is of thickness very thin. Very thin. It's not thick. It is very thin. The thickness is of 2.1 into 10 to the power minus 7 meters. This is the thickness of the gold foil. So what happens is when it is very thin, the gold foil is very thin, so multiple scattering can be avoided. It's so thin that each layer has got only one atom, so multiple scatter can be avoided. So by this, multiple scattering can be avoided. That's point number 1. Okay. Then point number 2, they use gold. Why do they use gold? Because gold is a very heavy atom. Heavy atom. Alpha particle is a very lighter atom and compared to gold, it's got 4 only as a mass, 4U as a mass. Okay. So when this collides with the atom of gold, it doesn't shake the gold foil. So then that's the the gold foil remains stationary. Don't say shake, it looks bad. So then say that the gold foil remains stationary even when the alpha particle is bombarding. That is another reason why we are choosing gold foil. Are you clear? These are the this is the details that you have to write on the Rutherford experiment. Then is the distance of closest approach. Sorry, this distance of closest approach. You all know that the nucleus is also positively charged. Yeah. The atom is of course there, but we are talking mostly about the nucleus here. The alpha particle is also positively charged. So when they come here, this is the closest distance beyond which it's getting rebound. It can only approach the nucleus only to a certain distance r naught. That's known as the distance of closest approach. Okay. So then that distance is r naught. You know the entire kinetic energy here is getting converted into potential energy. Kinetic energy formula is half m v square. Potential energy formula from the first lesson you know is k ze square, because gold foil is ze. Z is the atomic number and E is the number of electrons. So gold foil has got total charge to be Ze. Alpha particle has got 2 charge. So 2E. So it's 2Ze square by R square. That will be the kinetic energy is equal to potential energy. Okay, so this is the distance of closest approach, which is R naught. So the R naught square, Kz square by potential energy is R naught. Not this is a potential energy. Potential energy is K into Q1 Q2 by R. So this only R naught here. Are you clear? So from this you can write a formula for R naught. What is R naught therefore is K is 2Z E square by half M V square is the formula for R naught, which is the distance of closest approach. Okay. So next is, so then R naught is the distance of closest approach. By this formula you can get kinetic energy is equal to potential energy. This is the distance of closest approach. The two can go up and you can write the formula. So this can also be written as R naught is equal to K2Z square by kinetic energy. You can also write it like this. That's about distance of closest approach. Next is in the distance that R naught is, it seems as 41.3 for me. Can't remember so much, so leave it like that. Okay, so then let's go to impact parameter. What is impact parameter? Impact parameter engadhu enadunna, supposing this is the trajectory of the alpha particle. An alpha particle is going like this. This is a velocity vector v, and this is the nucleus. From the center of the nucleus, this distance is b. The perpendicular distance between the trajectory of the alpha particle and the center of the nucleus is known as impact parameter, b. And that formula for b itself is similar to this R naught, because it's approaching closest and rebounding marida. So you can use the same formula but with the cot theta by 2. So they will, for some reason they will not write this 2. Okay, they will write K Z E square, K Z E square by kinetic energy into cot theta by 2. This is the formula for distance of closest this is the formula for distance of closest approach. The formula into cot theta by 2 will be the formula for impact parameter. They have just experimentally written this, and you have to justify this. See, using this is B, and this is the angle, this is the angle of scattering, theta, angle of scattering theta. Suppose this theta is 0, which means the particle is going to go undeviated, correct? If theta is equal to 0, you know cot theta, you know tan 0 is 0. A cot 0 is infinity. Therefore, B will become larger when theta is equal to 0, which means B is equal to larger, which shows that supposing there is a nucleus like this, there is an atom like this, where there is a nucleus in here. When an alpha particle is coming like this, the distance between the center and the alpha particle is larger, it is going to go undeviated. It's going like this. It's going to go undeviated, and then slight deviation like this, and then the closer it gets, it's going to get largely deviated, and finally it's going to get rebound. So then when theta is equal to 0, which means the angle of scattering, that refers to this line where it's going undeviated. Where b is infinity, it's not really infinity, it's a larger value. It means that b is very large, it's away from the nucleus. Okay, when theta is equal to 90, theta is equal to, let's do 180. Theta is equal to 180, which means the angle of, it's getting rebound probably. Theta is equal to 180. This cot theta by 2 will become cot 90. It will become cot 90, and cot 90 itself becomes 0. That shows that b gets to 0. B gets to 0, which means there's no distance between the center and the trajectory, and that happens to this rebounding thing. Yeah, so these two analysis you can do as to b becomes 0 and b becomes larger based on this formula, and that is what is impact parameter. If they ask you to define impact parameter, it's the shortest distance between the trajectory of the alpha particle and the center of the nucleus. Shortest distance or perpendicular distance, and the formula itself is the closest distance, so the same formula with a cot theta by 2. There's no 2 there. Ideally there should be a 2, but they seem to have ignored it. And this kinetic energy, which can also be written as half mv square, okay, cot theta by 2, and that's the explanation for impact parameter. Write a note on impact parameter means this is what you should write. So can I go to next? So the Rutherford's conclusions. So conclusions I already said. Empty space, nucleus occupies very small radius, which is 10 to the power minus 15, where the size of the atom is 10 to the power minus 10, and it is positively charged, occupying the center. That's why a very few particles only got scattered and all that. Now the limitations of Rutherford. But limitations, Rutherford couldn't explain the fine spectral lines. The spectral lines could not be explained by Rutherford. He could not explain. That was a drawback. And Rutherford also said that the nucleus occupies the central part with a very small size, and the electron clouds are around the nucleus, forming an electron cloud around the nucleus. The electron cloud around the nucleus is what he's saying, which means the electrons will eventually lose its energy. See, supposing the electrons are spiraling around the nucleus, means it's moving around the nucleus, it will radiate energy and finally spiral in and fall into the nucleus, thereby making the atom unstable. Therefore, he could not explain the stability of the atom. He could not explain the stability of the atom because he just says electrons are revolving around the nucleus. Yes. He doesn't, which means electron can spiral in, losing energy, and fall into the nucleus, thereby disintegrate the entire atom itself, making the atom unstable. So these are the two limitations of Rutherford. Here comes Bohr, is a very important scientist, where he said 3 postulates. First postulate is, yes, it's right, the electrons are revolving around the nucleus, yes, but in a stationary orbit, which means it will have same energy level will be the same, energy level of each orbit being the same, So that's the first one. The electrons are going to revolve around the nucleus in a stationary energy level, which means it is not radiating energy, so it will not fall into the nucleus. Thereby that stability is achieved, point number 1. But in every postulate, this is the first postulate of Bohr. Every postulate I will support it with a equation. So what is that equation? So electrons are revolving around the nucleus, and the centripetal force in any circular motion, you will have centripetal force mv square by r, which will be equal to force of attraction between the nucleus and the electron. What is the force of attraction? K Z E square by r square. One second, hold on. So then first postulate formula explanation is they are held together by force of attraction, which is K Z E square by r square, which is equal to centripetal force mv square by r. So r and r get cancelled. Yeah. So in the equation you should know, this is the first equation from which you can find out what is r. From this you can cross multiply and get what is r. So this is the first postulate. What is the first postulate? The electrons are revolving around the nucleus in a stationary orbital. Am I recording? So that it doesn't radiate energy. So the centripetal force is equal to the force of attraction. Are you clear? That's the first postulate. Second postulate is the angular momentum of the revolving electron. No, the second postulate is not about angular momentum. Jump from the electrons jump. The angular momentum of the revolving electron L is an integral multiple of Planck's constant. L is equal to nh by 2 pi. The revolving electron or angular momentum is always above the head. If I'm spinning like this, above my head is angular momentum. Angular momentum is equal to integral multiple of Planck's constant, where h is a Planck's constant. So where n is equal to 1, 2, 3. So that's the second postulate. The third postulate is the electron can jump from a higher energy level to a lower energy level by releasing energy in like pockets of energy known as quanta. The electrons can jump from a higher energy to a lower energy level by releasing energy in the discrete pockets of energy known as quanta or photons. Okay, so that's what it is. So it can jump from higher energy to lower energy by releasing energy. But it has to jump from lower to higher, it needs energy. So these are the three postulates of Bohr, very, very important. First postulate being electron revolve around the nucleus in a stationary orbital, where the centripetal force is provided by the force of attraction. Yeah, so the next is the angular momentum of the revolving electron is an integral multiple of Planck's constant. Third postulate is the electron can jump from a higher energy level to a lower energy level by releasing energy in the form of pockets of energy known as quanta or photons. Okay, so E2 minus E1 is equal to h mu. So these are the three postulates. So you know these formulas, this is a mathematical expression, is mv square by r is equal to k z square by r square, and L is equal to nh by 2 pi, and E2 minus E1 is equal to h mu. These are the three with which we are going to start deriving the entire lesson. So let's first write the first postulate, which is mv square by r is equal to k z e square by r square, where r and r get cancelled. From this, write what is r, which is k z e square by mv square. Mark this as equation number 1. What is the second postulate? You know L is equal to nh by 2 pi. L itself is angular momentum is r times linear momentum, which is r into mv. Okay, so you should write r into mv is equal to nh by 2 pi. From this, write what is r, which is nh by 2 pi mv. Mark this as second equation. First equate the first and the second, because both of them are r. So k z e square by mv square is equal to nh by 2 pi mv, where v and v gets cancelled. M and m also get cancelled. From this you can write what is v. So cross multiplying, v will be k z e square by k z e square into 2 pi by nh will be v. So once you, this is your third. Once you get the third, substitute that in the second. So r is equal to nh by 2 pi m v ke badala this, which is k z e square 2 pi nh. So then r will therefore become, you should mark this up, n square h square by 4 pi square m k z e square. This r oda value. R is equal to n square h square by 4 pi square m k z e square. So this is the value formula for r that you get. Okay. So supposing in the r oda formula kadachirudhilla n square h square by 4 pi square m k z e square. Okay. You should know that for a hydrogen atom which has got n is equal to 1, so you can see that h is a Planck's constant. Okay, 4 pi square is a constant, k is also 1 by 4 pi epsilon, which is a constant, correct? Z, if it's a hydrogen atom, Z will be just 1, E is just a charge of an electron. Everything seems to be a constant, so R is therefore proportional to n square by m. Even in fact for hydrogen atom, m will also be constant. So R is just proportional to n square. Can you see? R is proportional to n square. So then they are saying that this value itself is 0.53. So R is equal to R naught into n square. R is equal to R naught into n, where this whole group constants together form R naught, whose value itself is 0.53 Armstrong. So R is equal to 0.53 Armstrong into 10 to the power minus 10 into n square. So for what is the radius of second orbital? Put n is equal to 2. N is equal to 3. You get the respective radius. If R is equal to 1, it will be 0.53 Armstrong, which will be the radius of the first octet of the hydrogen atom. That's known as Bohr's radius. When you put n is equal to 1, it means Bohr's radius, whose value is 0.53 into 10 to the power minus 10, or 0.53 Armstrong, or 5.29 into 10 to the power minus 11 meters. Any way they can say. So are you clear? So this concludes that R is prove that R is proportional to n square, means this is what you should write from starting from here. So now that we found R, n square by 4 pi square m, k is at e square. So that formula you need to memorize. Okay, next is, we know therefore with this we can find what is the radius of any octet, because R is equal to R naught into n square, which is 0.53 Armstrong into n square. Any radius of any octet can be found out. Like an electron is in the 4th excited state, n is equal to not excited state, ground state. N is equal to 1 stands for ground state, n is equal to 2 stands for first excited state. So n is equal to 4 stands for third excited state. வந்து சாப்பிட்டாங்க பசங்க. நிறைய இருக்கு. Thank you so much. Okay, please eat. Okay, eat and go compulsorily. Compulsorily. Okay, that's what I'm saying. You can keep eating and listening. Okay, so then continuing with what I'm saying, it's about.
Oh, nice.
Okay, please, because we're not supposed to eat so much. We're older people. So, okay, coming back here. So, you know, R naught, which is the radius of any octet, can be found because R is equal to 0.53 into n square. Similarly, if they ask you to find the velocity of any octet of the revolving electron, you should know, right? You know the formula for velocity itself is this, which is this, correct? Yeah? Take this formula and write it here. V is equal to 2 pi k z e square by nh. Take this formula and write it here. Multiply and divide it by c. Multiply this and divide it by c. V is equal to, and take the n outside. It's multiplication only, c by n outside. 2 pi k z e square by ch into c by n. Take it in that format. This itself is a constant. And this constant, it seems, is 1 by 137 into c by n. So, if you know, if n is equal to 1, then it's c by 137. That will be the velocity of the first octet. If n is equal to 2, therefore you know that velocity is generally inversely proportional to n. The velocity of any revolving electron is inversely proportional to n. The radius is directly proportional to n square. These conclusions can be achieved by this. You have to remember the multiplying and dividing by c, for which you should know the velocities formula. How will you remember the velocity formula? I cannot remember. Every time I can't remember. I only remember R is equal to n square h square by 4 pi square m k z e square is all I remember. So if I have to remember velocity, what do? I know that I'll quickly do mv square by r is equal to k z e square by r square. R and r get cancelled. R is equal to k z, no, r is equal to k z e square by mv square. Correct? First equation. Second equation is L is equal to nh by 2 pi. mv r is equal to nh by 2 pi. So r is equal to nh by 2 pi into mv, equating this and this. K z e square by mv square is equal to nh by 2 pi mv, and then quickly write what is v. That will be this. Okay, the only way. And then multiplying, dividing by n, grouping the c by n, rest of it is 1 by 137 into c by n. That's inversely proportional to n. Are you clear? So these are the formulas that you need if you have to derive or if you have to do the sums also. Okay, next is about total energy. You know there will be kinetic energy and potential energy of a revolving electron. Okay, and to get a kinetic energy of the revolving electron, you know it's half mv square is the kinetic energy, right? All we know is mv square by r, right? The first postulate. mv square by r is equal to k z e square by r square. R and r square get cancelled. Multiply both sides with a half. So half mv square therefore is k z e square by 2r. So this kinetic energy formula itself we got is k z e square by 2r. How to take the first postulate and arrive at kinetic energy. Once you get the kinetic energy, you know the potential energy's formula itself from the first lesson is minus k z e square by r. K q1 q2 by r will be negative, remember? So minus k z e square by r is the potential energy, which you already know. The total energy therefore, can you see from here to here there's a relationship? This is 2r and this is r. So if you want potential energy is 2 times the kinetic energy and with a negative sign. Can you see? Potential energy is minus of 2 times the kinetic energy. 2 and 2 get cancelled. So that's one conclusion that you get. And the total energy is nothing but kinetic energy plus potential energy, which is k z e square by 2r minus k z e square by r. The LCM for this itself is 2r. So we're multiplying this with a 2. So it's minus k z e square is the total energy. which is nothing but the negative of the kinetic energy. Kz square by 2r, this also Kz square, but it's negative. Therefore, total energy is negative of kinetic energy. Very, very important conclusions. They'll give you kinetic energy, they'll ask you to calculate the total energy. Or sometimes they'll give you total energy, they'll ask you to calculate kinetic energy. Even potential energy is negative of 2 times kinetic energy. All this will come in sum, so you should know this. So this is very important. Okay, so next is, now that we come to energy. What is the total energy? You know, is K is minus Kz square by 2r, right? That total energy itself is minus Kz square by 2r, where r itself is n square, h square, 4 pi square m k z e square. You get the total energy's formula to be something like this. Yeah. The total energy itself is minus k square z square e to the power 4, yeah, 4 pi square m, correct? Consolidated by 2 and 4 will get cancelled anyway, n square h square. So the total energy's formula is so much. Can you see? You can group all this and write it as minus 13.6 by n square, because all of these are just constants. So for a hydrogen atom, you know, Z will be 1, E will be 1.6, mass of the hydrogen atom. Yeah, mass of the hydrogen atom, you know, is like a mass of a proton, because nucleus consists of only proton, doesn't have a neutron, which is 1.6 × 10 to the power minus 27 kg. Everything you know is just, it's minus 13.6 by n square. Electron volt will be the total energy by n square. So if n, let's consider this as En. So if E1 is the energy level of the n is equal to 1, first octet, will be minus 13.6 electron volt. So n is equal to 2 will be E2, which will be minus 13.6 by 4. What will be the value of this? 4 3s are 12, 4 4s are 16. Minus 3.4 electron volt. You need to memorize all this value. N is equal to 3 is E3, which is minus 13.6 by 9. 9 1s are 9, 45. 9 5s are 45. So approximately minus 1.5 electron volt. N is equal to 4. It's minus 13.6 by 16. 4 4s are 16, which is 0. What will that value be? It's 136 by 160, correct? It's 0 point, means 1 0 will be added. 160 into what will give you? 10 will give you 160 into 8. Say 8 zeros are 0, 8 6 are 48, 8 1s are 8. Yeah, 1280. If you add a 160 to it, it will go more than that. 9s are 160 into 9s are 900, 9 6 are 48, 9 1s are 9, 1380. So therefore 0.8 approximately. Let's not write the whole value, okay? 0.8 electron volt. N is equal to 5, and so on. So thus you know the energy of every octet by using this formula. Okay, so next is energy of every octet in this formula. Okay, generally next is spectral series. Keep it like this, keep it like this. Now come to spectral series. Okay, you know that he is able to explain the spectral series quite well. Why? Because electrons, when jumps from a higher energy to lower energy, it is going to release pockets of energy, energy known as photons, which consist of frequencies and various wavelength. It makes sense that spectral series is formed. Okay, so coming back to your spectral series. Okay, there is a series such as Lyman. Okay, I forgot to continue with this. A little more I have to continue. Take this this formula of E. Okay, just take this formula of E, which is E is equal to, what is that formula? Is minus k square z square. Let's copy from there. Minus k square z square e to the power 4. Yeah, 2 pi square m by n square. Whole lesson you should by heart. You should be able to write it like a flow chart. That's when any question come, you can pick up from wherever you want. This is the energy formula. And suppose E, you know E is also h mu. E is also h mu. And mu is also c by lambda. E is also c by lambda. So it's minus k square z square e to the power 4 2 pi square m by n square h square. And you can write, you can take the h down, where it will become h cube. You can take the c down, where you can multiply with the c. So you get 1 by lambda, which is minus k square z square e to the power 4 2 pi square m by h square c into n square, correct? So 1 by lambda is nothing but the wave number, nu bar, h cube. Okay, 1 by lambda is nothing but the wave number. Wave number is mu bar, whose formula itself, you know, they are grouping all this to be a constant, which is Reynolds number. yeah, minus r into 1 by n square. They'll write it as Reynolds number, the value of Reynolds number is 1.09 into 10 to the power 7 per meter. The Reynolds number R is 1.09 into 10 to the power 7 per meter. Because you need this to calculate this, and you know it's minus R. Supposing it's jumping from, okay, normally it's jumping from a higher octet to a lower octet. It's the higher energy minus lower energy. So there will be n initial square, which is a higher octet, minus n final square, which will be the lower octet. Taking the negative sign inside, it's a negative sign inside, don't yawn, 1 by n final square by 1 by n initial square. I'm also putting in a lot of effort, so to respect that. So then finals n மேலேந்து கீழே குதிக்குது. இது in initial square minus final, it becomes like கீழேந்து மேலே குதிக்கிற மாதிரி இருக்கு subtraction பண்ணும்போது. Then final square minus n initial square மாதிரி ஆயிடுது. Where it's jumping to where it's jumped. From where it jumped மாதிரி ஆயிடுது, because I'm taking the negative sign inside. So now I can define the Lyman series, Balmer series, Lyman, Balmer, Paschen, bracket and Pfund. Paschen, bracket and Pfund. Lyman series is where it jumps from second octet to first octet, third octet to first octet, fourth octet to first octet. When it's from 2, always n is equal to 1. N in final is always 1. N initial may be 2, 3, 4, 5, etc. So in that case, it will be R is equal to 1 by 1 square minus 1 by ni square, where this ni may be 2, 3, 5, and such is called a Lyman series, when it jumps from any octet to the first octet. Lyman series will be list. Balmer, when it jumps from the final octet, n is equal to 2 is the final octet. It jumps from initial octet is 3, 4, 5, 6. From any octet to the second octet, Balmer series is released. So then that case, mu bar, which is wave number, is R into, what you get is 1 by lambda. What you get here is 1 by lambda. So you can reciprocal that to get the wavelength. Okay, so 1 by 2 square minus 1 by ni square, where ni may be 3, 4, 5. That's a Lyman series. So let's go to Paschen. Paschen is mu bar is equal to R into 1 by, you know, n final. N final in that is always 3. It's going to jump from n initial, which is going to be 4, 5, 6, dot, dot, dot. Such is called a Paschen series, where mu bar is equal to R into 1 by 3 square minus 1 by ni square. That's Paschen. Bracket is 1, n final is equal to 4, where R is equal to R into 1 by 4 square minus 1 by ni square, where ni may be 5, 6, 7, 8, Balmer series. Pfund is n final is equal to 5. Lyman, Balmer, Paschen, bracket and Pfund. Makes sense, right? So mu bar is equal to R into 1 by 5 square minus 1 by ni square, where ni itself is 5, 6, 7. That much clarity you should have. It's actually jumping from higher to lower, but when you substitute here, it becomes like lower to higher. Where it jumps to is first place. Okay, so that's so the CDs, and you have to draw these spectral series. Very, very important. One way of drawing, which is just for your own knowledge, that this is the this is the nucleus. This n is equal to 1. This n is equal to 2. N is equal to 3. N is equal to 4, and so on. Okay, when anything jumps from second to first, third to first, second to first, third to first, fourth to first, this is called Lyman series. Then they ask you to draw bracket. Lyman, Balmer. Balmer is like here, third to second. This is all Balmer. You can continue this diagram like this. You can also draw like this. It will be beautiful. If you see my video, I would have drawn something like this. It will be so beautiful. You can say Lyman, Balmer, Paschen, bracket and Pfund. But better diagram, they'll ask you to draw this every year. The board exam. See, this is it that I drew. Lyman, Balmer, Paschen. In like this I drew and explained. But if they specifically ask you energy level diagram, they specifically tell you to do energy level diagram, then you have to do a proper diagram, which is this diagram, where you know this is the ground state. Ground state is always referred to as n is equal to 1. Then you konja gap puttu n is equal to 2. Konja gap kammi panni n is equal to 3. Innu konja gap kammi panni n is equal to 4. Then closer n is equal to 5. Then still closer n is equal to 6. And still closer n is equal to 7, and so on. This is the ground state. You know, in the ground state, it's minus 13.6 electron volt is the energy level when is equal to 1. Then minus, what did we see? 3.5, minus 3.4 electron volt. Then minus 1.5 electron volt, minus 0.8 electron volt, and the rest of it you have to mug up. It's minus 0.54. Let's keep it as 0.8 and 0.5. Then minus 0.3, minus 0.2. We can't do much. So this is what I would like you to remember and write it like this. So these are the various energy levels. This is a ground state. This is referred to as ground state. This is referred to as first excited state. You should know when you say first excited state, n is equal to 2. You can't say n is equal to 1. This is second excited state, which is n is equal to 3. So if I'm going to do the Lyman series, Lyman is like tsh, 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 tsh. This is Lyman. Next Balmer. Tsh, 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 tsh. Balmer. Paschen, bracket and P-fund. Paschen, bracket, bracket, P-fund, and so on. This is P-fund. So you should know that can you see the spectral series? Depending on how it's jumping, you're getting different energy. Energy gap is different depending on where it's coming from. Based on that, there will be h mu. Mu itself is c by lambda. Depending on that, there's different frequency, different wavelength, and you get a spectral series. That explains how a spectral series is formed. Bose is very good. Can you see? This diagram is very important. You should know that this is ultraviolet region. Obviously, this will be next to ultraviolet is visible region. Lyman is an ultraviolet. Lyman Balmer is a visible region. This is infrared. Between ultraviolet and infrared will be visible. So then this will be near infrared and this will be far infrared. This is the water diagram. Everything is self-explanatory. Energy level diagram, you get full marks. They might ask you to draw this energy level diagram and explain. You don't even have to explain anything. You just write n is equal to 1, 2, 3 ground state. Everything is there inside. So you don't have to write an essay. Okay, this is your question. And all the energy levels are there. What else you need to write? Correct? So very important question. Now comes the limitations of Bohr's model. Limitations of even Bohr's model, in spite of the fact so beautiful, it's got limitations. What are the limitations of Bohr's model? Bohr here is considering only hydrogen. He's studying only for hydrogen atom, where he's not talking about electron-electron interaction at all, because hydrogen has got only one electron. He's talking only about an electron and a nuclear interaction. He is not talking about an electron-electron interaction, which means he's not studying for anything which is other than hydrogen atom. For a hydrogen atom itself, he is considering electron as the first octet, second octet, third excited state, fourth. He goes on in the different excited state, but he is not talking about a number of electrons being more. So that is the first demerit. Bohr is not giving justification considering other atoms. He is only considering electron. He is ignoring the electron-electron interaction by not considering and justifying for other atoms. He justifies it only with the help of hydrogen atom, which consists of only one electron and different energy levels. That's the first limitation. The second limitation is when there are, you know that there are spectral lines, right? Depending on the energy released. He couldn't, when he plays this, when he does this entire experiment in a magnetic field and electric field. In an electric field and in a magnetic field, he noticed that there are further splitting up of the lines. It's further splitting up of the lines, which is called Zeeman effect and Stark effect and Zeeman effect. Okay, Stark effect and Zeeman effect. Zeeman effect is in the magnetic field, and the Stark effect is in the electric field. He noticed the further splitting up of the spectral lines. The further splitting up of the spectral lines, well, noticed in the magnetic field.